Let's take a look at another hashing method. Let's look at open addressing hashing. So open addressing hashing should not be confused with open hashing, which is what we looked at previously, the method called separate chaining. This is an approach that allows the data to be stored anywhere in the table, and as such, it's called open addressing. That means we can place it wherever we want, and we'll have to have some mechanisms in place to actually deconflict where the data ends up. So since all the data is actually kept in the table, this is a form of closed hashing. Okay, so open hashing is when the data was stored outside of the table. Closed hashing, the actual data is stored in the table, and that there are no pointers where the data is stored outside the table. So when we actually calculate the hash function, if there is a collision, we have to resolve it by finding an open position other than the one that we hashed to. And I'll give you some examples that hopefully will bring more clarity to this. We will call h of k the home position. Okay, so that is where key k hashes in our function h. It's the original location where we would like to place k. However, if that location is occupied, then we will apply what's called a probing sequence. We'll look at a few different methods for probing, and we'll cover linear probing in this particular block. So what linear probing means is that if we hash our key k and we apply the hash function to it, and there is already a data item at that location, we obviously cannot store two data items in the same location, and so we will begin by adding a probe to h of k, and then we will normalize that sum, the sum of the original h of k plus the ith probe. So a couple of things are worth noting here. We always add the probe to the home position, and the home position is where the data would normally hash to once the hash function is applied to it, before any collisions take place. So the probes get always added. You notice that the probe, that this particular value is h of k plus probe 1, and this particular value is not the previous sum plus probe 2. It's back to h of k plus probe 2 all the way to the end, all the way to the nth probe, or the ith probe. It is h of k and an added function, a probing function. So the function p is a probing function, and the ith probe means this is the ith try of actually trying to store this data. So the first time we hash into a table, that is its home position. That is not a probed location. We only begin probing if there is actually a collision at that location, and then we will basically add our probe, our first probe. We will add that to h of k, and we will normalize. Normalize simply means mod by the table size. Okay, that's all normalize means here, because we need an index between 0 and m minus 1 if m is our table size in order to be able to store the data. So probing then is done until we find an open location, until the index wraps around through the original hashing location, i.e. the original home position, or until we have exhausted all possibilities at rehoming this particular item. That generally means that our hash table is full. And so there are multiple methods for probing. The simplest one of these is called linear probing. So we will take a look at that in some detail in this block, and then we will look at quadratic probing next time. And we will also talk briefly about random probing. It is a method that's used and is pretty effective. So linear probing, basically to keep things simple, the probing function is just going to be the ith probe is I. So the ith attempt to basically store the key in the table simply adds I to the home position. If there's a collision at that location, then we will add the next probe to the home position. And if there's a collision there, we will keep trying these in turn until we ascertain that we cannot find a home for this particular item, or we actually do encounter an open slot for it. So we have to be mindful of when we've reached the end of the table or when we've wrapped around, and when to quit probing, because otherwise you can see that if P of I is just I can just keep trying forever, but it so happens that that's going to lead to me trying the same locations over and over again. So we have to keep in mind when we've wrapped around and terminate the probing at that time and decide that we cannot store this particular data item. So in the worst case, the search is going to terminate with linear probing only, and this is important to note. It will terminate at the location that precedes the home position, and I think the next slide will sort of add some details to that. So again, the important thing when you do probing is to ensure that you have a way of knowing when you've searched through every possibility, when the table is full, and when it's time to stop probing. So let's take a look at a probing example. Again, this is a linear probing example. And what we've got, so this is right out of your textbook. We have these particular data values, and so we're just going to assume that the subscript indicates where the home position is. And again, the home position is simply taking that data item and feeding it to the hash function, whatever that first value is that it returns, where it would like to store that data item, that is known as the home position. So we begin with A5, and we hash to the 5th location, and there's nothing else in the table, so we're okay with A5. It went into the right spot. We then take A2, and it hashes beautifully into location 2, and so we're fine here. And we take value A3, it hashes to location 3. Again, there's nothing magical here. What we're saying is that the subscript is where the data item hashes to. So we've got these 3 data items, and they're all placed in our table. Now let's look at the next batch of 3 data items. I now have to insert another data item, B, which actually hashes to location 5. Well, location 5 is already taken up by data A5. And so when B hashes to this particular location, I'm going to determine that that's busy, and I'm simply going to add 1 to the location, and then do my mod again. So I'm going to add 1 to the 5, I'll get 6, and then I will mod by the table size, and I will end up in location 6. Okay, so again, B5 would like to be right here, right? This is B5's home, but it can't be there because A5 is already there. So we add 1 to the probe, we normalize, and B5 is in our table. Okay, let's look at A9. Well, A9, the table size here is 9, so this hashes into location 9. There's no one else at location 9, so A9 fits into the table without any consternation. And then we get B2. Now you notice that B2 will hash into location 2. At this point, I determine that there's already a data item at location 2, and I add the first probe, i.e. I add 1. Well, there it hashes me then to location 3. Well, location 3 is already taken up, and so I have to add my second probe, i.e. adding 2, before I can actually home data item B2. Okay, so we'll just keep following that approach as we get data into the table. Okay, so let's continue with this example and look at B9. Okay, well, when I try to put in B9, there's already a value at 9, and so I wrap around to the beginning of the table. I add 1, that gives me 10. I mod by the table size, so 10 mod 9 is, I'm sorry, the table size here is actually M is 10. It goes from 0 to, M is 10. So it goes from 0 to 9, which is 10 items. Okay, so add 1 and I get 10, and I mod by, I mod 10 by 10, and that allows me to put B9 into location 0. Okay, all right, we've got one more data item. It's C2. It can't go here, it can't go here, it can't go here because there's already B2 in here. A5 is here, B5 is here, right? So it's way down here before I can actually place C2, okay, and actually insert it into the table. Now, you know, what are some problems with this approach? Well, hopefully you see that we've got some serious clumping going on here, and that tends to be what happens with linear probing. And so let's take a look at location 8 and ask ourselves, what's the probability that next item maps to 8? Right? What's the probability that the next item maps to 8? Well, initially you may just say, well, it's 1 out of 10 because, you know, there are 10 slots here, and whatever would go in here has a 1 out of 10 chance. But it turns out that everything above it would actually map here. Anything that goes to 2, 3, 4, 5, 6, 7, or 8 would all map to this particular location. Okay, so we've got 1, 2, 3, 4, 5, 6. There's a I believe a 70% chance that the next value. So the answer to this thing is 70%. And again, how do we do that? We assume that a data item has the equal chance of getting mapped into any location. So there's a 1/10 chance for each of the thing that would go at 2, 3, 4, 5, 6, 7, and 8. So that gives me 70%. And let's look at location number 1. Well, it has a 30% chance, because if something maps to 9, I wrap around to the top and spot 0 is busy, and so I'll end up putting it here. So this has a 30% chance of getting filled in the very next with the very next data item, so that you see that we're losing that uniformity that we really wanted here. We wanted to have the data distributed uniformly across the table if possible, but really what we have is we have data that's in clumps, and clumps only tend to snowball